So, okay, let me just share some philosophies. Planet formation is a complex process, diverse, rich, and in-depth. So in that attempt, we actually try to fill out what is important. Everyone has his opinion. And they all want to emphasize the importance of their work. However, what is needed is really try to come up what is the overwhelming, the major big picture, and try to piece together incomplete information and come up with a simplest interpretation. So we have this tool, population synthesis model, which I would want to impress you, is a tool to understand what we don't know, to explore new territory. It is not to be used as a gadget to fit everything with infinite number of knobs. The basic concept of theory of planet formation was laid out long before there was any observations of disks, and perhaps there was a sort of a interpretation of this because all of the planets in the solar system lays in the same plane, and that's how it was initially contrived. When I was a graduate student, we did not have any evidence of gaseous disks for another 10 years. But that did not stop us from doing theory, and the role of theory is to identify some fundamental big picture issues, okay, and try to understand diverse physical process, build up repertoires. So many people they made two comments about what we do, is that we can always come up with an interpretation on any observation. That is because we've been working on these subjects for a long time. There's a huge buildup of a repertoire of ideas. So when what we don't know is a boundary condition, and when you put those boundary conditions together, immediately we can piece missing information together. The second thing is, observers always accuse theorists that they see it when they believe it. I would accuse observers the same thing, as I will show you. Now, today, in the age of discovery, we have advancements in three fronts, okay, both in terms of characterization, discovery of exoplanets, in the search for star formation, protostellar disks, and solar system exploration. All of these advancements bring together different pieces of information. Whereas solar system exploration gives us precision relic information from which we can really do archaeology. And exoplanets give us a census of what is going on right in this environment, whereas star formation tells us some ongoing process where we can test some of these ideas. And I think the greatest gift to people like Chas and me over this course of our career has been the great advancement in all these fronts. The role of observation is to establish the existence and non-existence of phenomena. It's a very Buddhist philosophy here. And to identify what are the common features and versus exceptions. You know, don't just always shout, what about this? And you explain that, what about this? Well, this may not necessarily be the dominant effect. So to clearly state the precision limit and selection effect, we just heard from Deborah, all of the problems that could go into it, and what is believable, what is not, and perhaps we should really step back for a moment to think out of the box and to explore uncharted waters. I think what I really want to bring across a message is to be open-minded and avoid over-interpretation. Okay, so in this piece, and I have already talked about the different approaches, big picture is important, and the question is whether when we looked at the distribution of planets today, is it nature or nurture? Is it the way that they were born, they were evolved, they interact, or is it something that tells us is observational selection effect? Okay, so the challenge to link theory and observation together is that we have many observational clues, and from these clues we can then bring together and match together with the theoretical repertoires, ideas, but it's important to keep in mind one need to take a holistic approach. You are not going to be able to explain every detail. You can only give overall big picture, do a synthesis, and to get some clues. Now, we have seen this many times, and the message I take home, the very simplest message I take home from this is that super Earths are very common, and whereas gas giant is a marginal case. And their structure, the planetary system structure, are very diverse, and so we have heard a lot of theoretical ideas here and some discussion, and some people will want to explain solar system in the most glory detail possible and come up with version 15.5 of the NICE model, and try to give you, constantly ask the question, does your theory of planetary formation for exoplanets explain the solar system? Well, does anybody's biology, molecular biology theory explain the existence of you? So that is not a good question. You have to ask what aspect you want to explain. I can explain perhaps evolution of human population, but I cannot explain the psychological state of Chas Beichmann. And so, what do we want to focus on? Okay, here is solar system exploration. We have learned enormous amount from that, from meteoritics to geology to atmospheres, magnetic fields, you name it. So what do we learn from this? Well, we learn something about timescales, right? We can look at the meteoritics. We learn that there is some constraint on when pieces of these rocks in here was formed, okay? But we have to keep in mind that these rocks came from one special location in the solar system, namely near the asteroid belt. Now, they tell you something about timescale, maybe 2 million years between CAIs and also chondrules, but everybody tried to use that as a constraint on the timescale of planetary formation. But is it? Because if we now look at the evolution timescale of things like protostellar disk, and we see there's a general trend, the depletion timescale is a few million years. This has been a constraint for us. However, now this is measured. What is significant is that these data points are centered around individual clusters, which there are many members. In the same cluster that has many members, sometimes you see 50% of the star have disks or signature of disks, 50% don't. That tells you that the evolution has a large dispersion in their timescale. Secondly, many of these observations may have some observational dispersion in their sensitivity, And so we need to explore this further, but there are a lot of dispersions. We don't know very much about the total mass of these systems. We do know the size of the disk has a large range. The amount of total angular momentum in these systems, in the disks, can vary by 3 orders of magnitude. Okay, and we know that their accretion rate can have large dispersion. So we need to fold in all of these parameters in our determination of what is the most likely outcome, but not the unique outcome of planetary system. So while almost all of the material that goes into the central star goes through the disk, and some of this material is left behind to form planets. I talked about this on Tuesday, and I said only a small fraction of the mass is left behind to form planets. In fact, you could do this test by looking amongst members of open clusters, young clusters, to look at their dispersion in the metallicity, and iron especially, or look at binary stars. You don't even have to look at binary star with planets. You can see whether there are any dispersion in their metallicity. This is important because it tells you how much heavy elements you can get left behind. Why is that important? Because that will tell you whether planet formation is a robust process. If I have to say that based on the minimum solar nebula hypothesis, that I utilize all of the heavy elements efficiently, then I got to find a way to put them into planets. As we see, that when you look at planetary system and from Kepler's data, okay, while gas giants are primarily found around metal-rich stars, super-Earths are found around stars with metal-poor host stars, and so they're equally likely to be formed around here. So, and the total mass of these super-Earths in some of these multiple systems, when you add them up, their mass is in excess to the critical mass core that you need to form gas giants. It tells you that the formation of planetesimals is a robust process. It does not depend on the metallicity of the disk. So if you can come up with many theories, many models that tells you that you have to go over a certain metallicity before planetesimal can form, and then you can point towards these observations and try to extract information. None of these arguments are acid tests, but all of them provides you with a circumstantial evidence when you build up these evidence, and they tell you something about the process of planet formation. It is well known that the occurrence of Jupiter, for example, increases with the mass of the host star, although this part is somewhat controversial, and increases with metallicity of the parent star. These results came early because we only know about gas giants. And so we were focusing on what is needed to form gas giants. And we tend to make this assumption, this underlying assumption, a fixed fraction of the total mass in heavy elements in the host star is left behind in the disk. Now, metallicity of the star. Metallicity of the star does not represent the metallicity of the disk. Just because a star has a larger metallicity, it does not mean that you have more building block material to build planets. In fact, you may even have less, because whatever you did not leave behind in the disk went into the star. So if you left a lot in the disk, then the star should be metal poor, not metal rich. there is no reason why stars with more mass necessarily would have a higher, a more massive disk. In fact, these disks don't last very long around massive stars. So it depends on which stage that you are actually doing the planet building process. These are uncertainties that is in our model. We need to work on this. So there's one type of model that I introduced to you on Tuesday with regard to looking at migration as a criteria to get to overcome this merger barrier, and we're able to construct these match with observation, but that's just one model. In that model, we have made assumptions. We continually question every assumption we make. Okay, so in the early days, when we looked at migration, we look at this mass period distribution, and we see there is a paucity of gas giants around here. So there's two types of migration, the gas giant migration and the super-Earth migration, type 2 versus type 1 migration. But when you focus on this, well, we take for granted the observation is complete, that we have everything that's there. Now that needs to be questioned. Suppose it is. And then we try to work out this migration along the way that the disk is being depleted. So you look at the relative depletion time scale compared to the migration time scale. You can utilize population synthesis model to do this as a generic tool to learn something, okay? Or alternatively, you go into building a model of the disk from first principle. You should do both from first principle and then see whether you can accommodate this type of observation, okay? What we find is that there's a crisis, that the standard accretion model that's been worked on for a long time seems to indicate type 2 and type 1 migration tends to go too fast. And that challenge has brought us with a huge amount of new work, and people try to do fundamental research to look at the planet-disk interaction and how to go forward. Likewise, from this type of population synthesis model, there's a lot of rich information in here if we have a complete sample of statistics that we can trust. If you have that, then the upper boundary may tell you how the planet gas accretion stops, and the lower boundary, if there's indeed a desert, may tell you something about how they initiate the gas accretion process and how they initiate the migration process. Okay, now the outer boundary may tell you something about when they built these cores, and because that at these locations, any residual planets or planetesimals may get slingshotted out like the Oort's cloud comets or Kuiper belt objects, simply because gravitational assist will lead to the ejection of many building blocks. Okay, so on the inner boundary, it tells you something about how they may stop. So these type of tools that you have been using over the last week, it's incredibly useful for us to try to explore physical ideas, not just to fit with observations. Don't jump in there too quickly. Okay, so I talked about migration. For example, I mentioned that this challenge, this migration is too fast. We have to recognize that fact. And you have now to come up with new type of attempt and try to understand whether there's a way to get around them. And this involves understanding this structure better, tidal interaction better, and so on and so forth. We're starting to get a control sample, and we see there's distinctive difference between the gas giants and the super-Earth. But is it? Just this week, we know there's a new set of release that shows that this region is now populated with a lot more new data. Are we really looking at a complete sample here? And that we require the observers to have a dialogue with us and to tell us what is believable and what is not. Okay, maybe not believable, at least we should take it with a grain of salt. As all observers always take theory with a grain of salt, and we should do likewise. All right, so these things, as I said, migration is important, but more important is how you stop. I learned that when I was on the ski slope. In fact, I learned that when I was on the ski slope with Deborah Fisher. I didn't know there were so many vocabularies in her repertoire. And but this tells you about how things can move, how things can stop. To understand how things stop, we need to understand the central star while they're young. And stars which may have magnetic field, they may influence the inner structure of these disks. So this is new territory. And despite the fact for 40 years, we know about the physical process of magnetosphere disk interaction, and there has been relatively little progress. It's because this process is very difficult to understand. Most people would just dismiss it. If you have to go to magnetic fields, then let's forget it, okay? But magnetic field is everywhere. It is important. The problem does not go away just because we want to ignore it, okay? Magnetic field is not the haven of the squandrum, the last haven of the squandrum. It is there. You have to face it, okay? And one has to understand what's going on. As Deborah was so explicitly expressed. I don't know how I can repeat that better. Okay, so magnetic fields. What do we know about magnetic field? There's a in-depth study of these magnetic fields by looking at measurement of magnetic field in the T-Tauri star, and looking at their rotation rate, looking at their sizes, accretion rate, and they're all correlated in some way. Some of them have magnetic field with no accretion, some of them have accretion. So what's going on there? Is there a magnetic gate that is allowing material to flow through? Is there time-dependent variations that one can understand? And here again, theory and observation need handshaking. Here is again an observation or model interpretation of observation. And this is exactly reflects the uncertainty. Now, Rebecca Dawson drew this from the earlier release of Kepler, right? So now, first of all, it is important not just to say Fe over h greater than 0 or less than 0. What about 0.01 versus minus 0.01? Okay, you would have put them into different samples. But the uncertainty is larger than that. So one should really be a little bit more fair looking at the whole distribution as that. And furthermore, when we see the new data, look, there's a whole bunch of new things right around here. If I look at the density of the blue dots and the yellow dots, there are more yellow dots here than blue dots. I cannot believe this is produced in the last quarter of the Kepler mission. So that is a man-made or human-made cut. And that cut, we cannot really rely on theoretical interpretation when there are uncertainty introduced by that cut. Okay? So there is an interpretation here, we heard yesterday, that there is a paucity of planets around here. The current interpretation is that these guys have been evaporated and they have lost a lot of mass. But there are a lot of these guys up here, and their density has a large dispersion. Now, on the ski slope, there are double black diamonds that steepen into cliffs. When you lose mass from a gas giant, you steepen into a cliff. Because you lose mass, the gravitational potential becomes shallower and shallower. You start to lose more and more mass. You don't stop with a few percent gas in your envelope. You go all the way. You go down to here. So how is it possible that you can lose mass from here and go down to here and you lose 50%, or you lose, let's say, you lose 100 Earth mass of gaseous envelope, only to preserve the last 5 Earth mass of gaseous envelope. My interpretation is that they didn't go up that way, not that they came down that way. Be open-minded to sort out this particular, these diverse scenarios. Another thing that we talk about is the possible formation of multiple systems. There's no shortage of multiple systems, especially amongst gas giants. When we look at the gas giants, there are many multiple systems, and these multiple systems, when you look at them, the large dots are the multiple systems. When they go into long periods, they have large eccentricities. Dynamical interaction, instability, dynamical instability, and we should be able to get this eccentricity distribution, all hell should break loose. And we have plenty of theory to produce that, okay? But you start with an arbitrary initial condition. I would say that planet formation did not pick arbitrary initial condition. It emerged out of gas. There's a lot of dissipation that occurred. So when there's a lot of dissipation that occurs, there are islands of stabilities that these planets can settle down to, that they don't just go randomly out of blue and go everywhere. Now, here I also plotted around here, it's a different color for the planet, okay? Most of these guys are gas giants. But when you look at most of the low mass objects, the black, the mass cannot even be determined in many of these systems. And when you look at the low mass object, the eccentricity are pretty low. But there's no shortage of low mass objects. Let me go to here. That are in multiple systems, and they are in damn packed multiple systems. They're so packed that you put in one more, they become unstable. But they are so common. So it's not by accident that they can be so packed like this, but they're not having a riot, okay? And that they manage to get into this environment. This is a challenge for theory. We don't take it at a face value. We got to go down one level deeper. And what is going on here? To understand whether they're like this or they're groupies, we need to understand from observations. But the observations by looking at their space, the distribution of their spacing. But these observations are plagued with observational selection effect. Before we can do that, we need to understand these observational selection effect, because what is determined is the larger distance between them. But when you have something that is larger distance for the transit system, you're going to miss it. Okay? Now, we also heard yesterday or day before, there are two classes of these super Earths. 45% of them are in multiple systems, coplanar. The other 55 are not. Be careful with that statement. The other 55, you found one planet. You may find some perturbation to that planet. There may indeed be some false positives. We have no idea, we have no proof yet that they do, that 55% are in multiple systems that's not coplanar. We don't know that, okay? So, but if you can establish that, that would be fantastic because it will provide a new input, a new aspect of the Pandora's box that we have to explore. Okay, let's go on. Rossiter-McLaughlin effect has been used as an acid test to show that this migration is not the dominant effect for hot Jupiters. And this statement, when it was made about 10 years ago, the first time, I challenged immediately, okay? Because the interpretation is that you can have these dynamical instabilities, and then they will relax, and there will be scattering that gets into the center. And the assumption is that the disk and the star always have the same angular momentum. That's a wrong assumption. The star in the solar system, the sun, has less than 10% of the total angular momentum of the solar system, even though it has more than 90%, 99% of the mass of the solar system. When you want to change the orbit, you're not changing the mass. You're changing the angular momentum. It's much more difficult to change the angular momentum of the planets than to change the angular momentum of the star. So if you're going to change the orientation of the disk, okay, and that those disks are connected to the star, when you change that disk, you're going to change the star. When you suppose there are other dynamical processes, other dynamical process includes COSI. We talked about COSI. Surely many of these things must experience COSI, must experience scattering. But are they the majority? Or are they the exception? COSI has no discrimination on what is the inner part of the star. The star can be low mass star or high mass star, all right? So we can scatter this in, but why is there this dependence? Because of tides. Tides, that interpretation of tides. When you have tides like this, and that tide would then cause most of these planets to decay in semi-major axis as well as eccentricity. Sorry, let me go back. It decays in semi-major axis as well as eccentricity. So the tides has some implications. You can say, oh, I just decay I just decay the obliquity. Okay, if you change the obliquity, you find there's a general tendency for obliquity to be either aligned or anti-aligned. We don't see that. There are also many systems, there are binary, there are multiple planets, and that is misaligned with the spin of the star. Surely, those guys cannot be scattered in. Some of them may not be even influenced by the COSI effect because they're separated by large distance. What about binary stars? Rossiter-McLaughlin effect was invented by 4 binary stars more than 60 years ago. Now, those guys surely cannot be scattered or by these type of COSI mechanism. And we see them. So is there an alternative? Is there an alternative? Well, the other thing that you want to say is that here observations can also play a major role from the effect. We heard from Scott and Christian about microlensing observations. We can look at whether there are indeed perturbers out there, and that can do the job of scattering, okay? And that can provide a constraint. I hope you'll find some, but you know, because my mind is open. And for that reason, I want to argue in this alternative suggestion. Here is something that Tammy Rogers has done, and that around these high mass stars, what she is proposing, it is the spin of the star that has changed, not the orientation, not the plane of the planet. And the argument is that they can generate internal gravity waves because in the core, there could be, I will finish in a couple of minutes. And there, in the core, there's convective core that pushes around the envelope, and that can excite waves which can propagate to the outer region, get dissipated there. And we see this type of phenomena, okay, and in a cat. You can do a cat experiment. I always encourage everybody to do this. And it may be a catastrophe, but you take the cat up to the 4th floor, and you hold it upside down, poor cat, and you drop it. And the cat is going to land on its feet. Okay? So there's, oh, poor cat. If you want to see a real movie of it, you can look on the internet. It's very well cataloged. And anyway, so there's no spin to begin with. There's no spin to begin with. There's no spin to end with. And there's no torque in between. So how did the cat turn around? Right? And if you have a camera that focuses on the head of the cat, there was a spin. Okay? And if you have a camera focus on the tail of the cat, there's another spin. The total angular momentum of the system is conserved, but the cat turned around because of this topology. Okay? We see this type of phenomenon on Earth. We always talk about weather. I got my degree from England. That's one thing I learned. So talk about weather. And so there is a phenomena called quasi-biennial oscillation on 28 months period that the jet stream changes course. And this is associated with this type of process. There's one way to test this idea, is that the spin may change direction over decades. So you should follow up with the Rossiter-McLaughlin effect and to check again to see whether it works. There is also an independent check from what we learned from Malcolm earlier. There are these stellar oscillations that you can measure, and you can look at these frequencies. There are big splits and small splits that are due to the rotational breaking of degeneracy. And because of that, you can probe the rotation in the core of these host stars versus the surface. And you should try to do that to see if there are differential rotation as well as differential obliquity. Now, the next I want to talk about, just 1 more minute, is this idea of a sweeping secular resonance. Now, when you look at the solar system, the Earth's form, the Earth's age is 30 million years after the CAI. But 30 million years, the gas is gone. So Jupiter has to form first. But Jupiter is further away from the sun. How can it form first, then Earth? Okay? It doesn't make sense. How can Earth form much later than Jupiter? And if you need a core to begin with. Now, there is a way to do it. It's because there are things like isolation mass, there are these dynamical effects, but more importantly, that Jupiter itself, is on a slightly eccentric orbit. The presence of the disk causes a precession. So the location of this precession introduces a secular resonance, and the secular resonance has a tendency to perturb any planetesimals in this region. So during the evolution of the disk, the location of the secular resonance has moved in from the asteroid belt into the inner part of the solar system. And along the way, you can actually produce collisions. You can clear out much of the asteroid belt, get a very well confined inner region. So this, you can do everything that the Nice model wants with Grand Tech without moving Jupiter by very much. Okay, from secular resonance. Why am I introducing this idea of secular resonance? Am I just following the footstep of Nice model and try to explain the solar system again? I'm just trying to say that this type of phenomena can work in the solar system, and we can also make it work. Whoops, what did I do? We can also make it work in extrasolar systems, okay? Fomalhaut and Vega. It is very well known in Fomalhaut and with Vega, and there are inner and outer disks which are separated by huge distance. And people came up with the idea that maybe there are 4 gas giants in here, and that clear out the gap. None of them have been found down to 1 or 2 Jupiter mass. But if you have 1, even a half Jupiter mass object that has an eccentricity that's similar to what you see out of the extrasolar planets, and that during the depletion of this disk, this is not a dynamical scattering, but during the depletion of the disk, the sweeping secular resonance would have propagated throughout this region, give you a clearing of this disk by almost a factor of 10 in the separation between the inner disk and the outer disk. This is a work done by Xiaochen Zhang and for her PhD. Okay, so let me wrap up. And I was supposed to talk about and solve problems. And there are many. None of the problems that I proposed to you, the explanation I proposed, are solved. They're at just a small step towards a progress. And because we still have to make assumptions, we should always come back to ask this question: what have we left out? And what assumption have we made? Can we go back to relax that assumption and look for alternative? To do that, and this is the purpose of this workshop, that we introduce this idea of the population synthesis model. It should be used as a discovery tool, okay, rather than a gadget that you just turn knobs and fit with observations. Because not only you don't know whether there are any uncertainty in the theoretical concept here, okay, you don't even know the degree of certainty from the observation. And the field is progressing, and you're very lucky, I am very lucky, and I hope I will join you in this path of discovery. Thank you. So the question is, the magnetic field operates on many scales and on many different length scales and time scales, and it's very complex. It needs huge amount of computational tools, and can we still make any progress? My feeling is that you can do it piecemeal. You don't have to do everything at once, okay? And we can try to address some problems. Reconnection is clearly a long outstanding problem in plasma physics, period. We cannot resolve everything at once. There would be people working on that, but there are also people who give a prescription of, or a range of prescription for reconnection and try to go on with that. And there are things you do with the magnetic field of the disk, magnetic field of the star, and magnetic field of the planet. All of these are worthwhile, and we should be able to even work out things like detectable signatures, such as from synchrotron radiation, whether we can detect that with next generation radio telescopes. I should have given her the microphone. The emphasis is on statistics, and because Planetary, both observations and theory, there's a considerable range of dispersion and uncertainty, and perhaps it's even intrinsic to statistical mechanics, because many of the things I talked about here is also a reflection of statistical mechanics. So, try to think of planetary system along the way of Poincaré rather than along the way of Laplace, who is deterministically minded, and then encourage this dialogue between theory and observation. Well, there are some attempts, and I think there's a poster given by Xiaojia Zhang, and you can, I would encourage you to talk to her. Okay, so the question is whether there are any attempts to understand why type 2 migration is not quite correct. And I just referred him to talk to Xiaojia. This is emphasis on the importance of revisiting the assumptions and the errors and various things. I'm slightly older than most people. And so I would say one needs to be an enthusiastic advocate, okay? And otherwise you don't, get attention and jump up and down and say, here is why this is worthwhile working on it. But so I have no trouble of arguing against Richard Nelson, at a very heated debate. But at the same time, I think in my own mind, I always know there's some degree of uncertainty. And I have to be honest to myself, even though I may shout him down. But I have to go back and revisit, and as you have pointed out.